Of course, today, the focus is going to be on variable selection. Okay, you know, when we're working with regression model, okay, we normally at times we had regressor, at times we had explanatory variable. The question now is, do we have a way to decide on the variables to include or to exclude from our model? Okay, so the focus today is going to be on variable selection. Okay, uh, do we have a technique, to select relevant variables into our model? Okay, so in the outline, I'm actually going to walk you through can we improve on ordinary least square? Can we have a way to improve on ordinary least square? Don't forget, ordinary least square is what the method that we use in estimating parameters in linear regression model. Let me tell you, the moment we got a lot of variables in the model, the ordinary least square may not perform well. And is there a way we can actually consider ways to improve on that? Okay, you're going to learn about that today. And of course, today you're gonna see the difference between module complexity and module fitness. The two are not the same. Okay, when do we consider module fitness? When do we consider module complexity? Okay, but let me tell you, in a modern day statistical world, we actually consider criteria that put into consideration both module fitness and module complexity. Okay, then I'm also going to, and those criteria, like I just said, our square, the AIC and the BIC, they are very, very vital in a variable selection. And of course, you're also going to learn procedure of variable selection from all subset selection and to stepwise or to stepwise regression. Let me tell you this, today what we want to do is very, very crucial in statistical world. So I need you to pay attention, okay? Now, let's start with the first objective. Can we improve on an ordinary least square? Why do we want to improve on an ordinary least square? Oh, I'm actually going to tell you condition under which you cannot trust your ordinary least square anymore. What do I mean by ordinary least square? The ordinary least square is a method of estimating parameters in a linear regression model. Okay, and that very method is going to break down under certain condition. But let me tell you this. Let me first identify when it's going to work great. Take a look at this. N is the number of observation. P, your P is the number of explanatory variables. Okay, situation where the number of observation is much more than the number of explanatory variables. Of course, the OLS work well. You know what I mean? The other time where I was using data on Rate My Professor, okay? We used the number of observation was 366. And the numbers of, maybe you have 5 numbers of independent variable. In that situation, OLS will work well because the number of observation is much more greater than the number of explanatory variables. Does that make sense? Okay, that is the situation where OLS actually work well, because it's going to work well. There's going to be low bias, there's going to be low variance, and your model will be highly interpretable. What do we mean by interpretation of a model? There's a lot of transparency in statistics, okay, compared to machine learning. In the machine learning, you don't know what happened within. There's something that we call a black box. Has anybody had about a black box model? Black box model. That's not transparent, okay? But what we do in statistics, highly transparent. Transparency implies interpretability. And interpretability is only going to occur when there's low bias, there's low variance, okay? And situation where n is much more greater than the number of explanatory variables. But what of in a situation where they are very close, okay? The least square will still fit the data, but it's going to have a high variance. And that may result in overfitting and poor predictions. Let me tell you this. If I want to work on predictions, I'm actually going to I'm going to split my data into training. Has anybody heard about that before? Where you split your overall data into training set and a testing set. A good number, a good number, a good percentage of data have to be committed to training, or maybe like 70 to 30 or 80 to 20. Okay. You want to learn your model from the data. And if you want to test the model performance, you're going to use the test data. Does that make sense? And let me tell you this situation where the number of observation is much more, it's more or less equal to the numbers of explanatory variables. Your model will do a great job with training data, but it's going to perform poorly with testing data, which means your model can only do a great job with your training data, but it's not going to perform well when you when you bring in a new data. And that doesn't make sense. It means your model cannot be generalized. In that situation, OLSC perform, but that will result to overfitting. We call that overfitting. Overfitting means high variance. High variance lead to overfitting. You know the meaning? What could lead to high variance? Because you got a lot of explanatory variables in your model. Because the number of observation and the explanatory variables are more or less the same. If they are more or less the same, then there are too many of that. Oh my God. Is it possible we have two captains in a ship? That would be problematic. Having so many variables in the model is going to be problematic, will result to high variance that we call overfitting. But this is the worst. I'm going to show you the worst right now. Oh my God. When the number of observation is smaller than the number of explanatory variables. That's not good. Your OLS is never going to work well. It's not going to be unique at all. Okay. And the variance is going to be infinite. What do we mean? When variance is infinite, the variance is going to be so high. When the variance is so high, then in that situation, you cannot prevent multicollinearity. I told you yesterday, the multicollinearity is when there's a relationship between, explanatory variable, which means two or more explanatory variable, they're actually giving the same statistical stuff. They are more or less the same. Okay, if they are the same, why did they have to be in a model? One have to go for one. Does that make sense? Okay, so I just identify situation where you can trust your OLS and where you cannot trust your OLS. Now, because of that, because number 2 and number 3 could lead to a situation where we can no longer trust our OLS. Okay, what do we need to do to improve on the OLS? Yeah. We don't need to improve on OLS in case number 1. OLS performs so great when the number of observation is actually much more greater than the number of explanatory variables. There's nothing to improve there. OLS is going to perform so great because you're going to have low bias and low variance. Okay, but situation in number 2 and number 3, what do we need to do? What we need to do, because our models are so complex, our models have a lot of variables in it, and some variables may not even be contributing. What are they doing in there? Because of that, we're actually going to consider subsets. We're going to have some solutions. Okay, these are the alternative. Alternative number 1 said consider subset regression. What do we mean by subset regression? Means look for a way to only consider variables that contribute and eliminate those ones that may not contribute. Does that make sense? That means we're not going to run a model with all the explanatory variables. We need to first conduct an analysis where we're actually going to eliminate some variables that may not necessarily contribute. That's what we call subset regression. And then another option is what we call a shrinkage. What do we mean by shrinkage? Coefficient beta, like beta 1, beta 2, and so on, they give us the contribution of those explanatory variables. Okay, can we have a technique where the coefficient of an of unimportant variable will be shrunk to zero? You know, when the coefficient of of a variable is shrunk to zero, you know what I mean? It means that variable is not important and it shouldn't be included in a model. That's what we call shrinkage. We have a method of shrinkage. Okay, in the shrinkage, that is where lasso regression and ridge regression will play out. Okay, the last one is what we call dimension reduction. We use this approach, okay, to resolve a problem of multicollinearity. Maybe we got a lot of variables in the model. They are correlating. Okay. How can we, and if there's so many variables in the model, the dimension is going to be high. What do I mean by dimension? Dimension is n multiplied by p. No, number of observation by numbers of explanatory variables. Then with this approach, we actually can reduce the dimensionality. Okay. Now, these are the three-way solution. You know, you can choose any of these. Okay. In the course of this lecture, you're actually going to see the one that's going to work well. Why do we need these three solutions? We need these three solutions, any of these solutions, you know, to resolve, to improve on our OLS, because the OLS is not going to perform great in these two scenarios. Okay. So, and that is the reason why you need to understand your data set. You need to, when you understand your data set, you'll be able to know when to use OLS or when not to use that. Okay. Now, I want to move right now. Now, model interpretability. Let me tell you this. When P is very large, you know what I mean by P? The number of explanatory variables. If it is very, very large in the model, even OLF is not going to be interpretable. Okay? Now, let me tell you this. When you have so many independent variables, okay, and you are using statistical model, there's going to be a problem and you will not be able to interpret your model. What do I mean by interpreting your model? It may be difficult for you to isolate the effect of each of the explanatory variable to the response because there's so many of them. Okay. And what do we do in statistics? We do model explanation. But do you know when that is great? Okay. Having so many variables in a model, you know where that is great? That is great in machine learning. Machine learning is not about model interpretation. Machine learning is not about model explanation. Machine learning is about prediction. Model prediction is even from model explanation. Statistics, we focus more on model explanation. And model explanation will mean your model will be interpretable. But in machine learning, okay, because they need so many parameters, they need so many independent variables in the model for them to have a great prediction. Then they can only talk about prediction. They may not be able to interpret, you know, they may not be able to isolate the effects of each variable. So model prediction is even from model explanation. Go ahead. Yeah, yeah. No, we have an approach that we do that. You're going to see when we go to shrinkage. Shrinkage means shrink the coefficient. When they shrink the coefficient to zero, okay, the one that have a coefficient beta equal to zero is the one that is not important, which means the method, you know, has already eliminated them. We have an approach, which I'm going to show you. Okay, now there will be some variable among it that are little. They have little or no effect. What are they doing? They need to be removed. Then the module will be easier to interpret if we could remove an important variable. That is from statistical point of view. Statistical point of view, where what we normally focus on is explaining variation in the response. To be able to explain variation in the response, you don't need so many explanatory variables because your model will, the interpretation will be lost when you have so many variables. That's why we're removing them. But in machine learning, okay, in machine learning, we don't do that. So machine learning, using the idea of machine learning and statistics, it depends on your intention. Okay, because science generally we have basic science and applied science. You know, the basic science is more or less talking about going retrospective. I want to understand the past to be able to explain this part. Explaining the part. That's a module explanation. That's what we do in scientific world. Okay. But in a machine learning world, it's forward looking. Forward looking. Okay, that's prediction. Now, I want to talk about shrinkage right now. The method that will shrink, the unimportant, the coefficient associated with with unimportant variable to zero. Okay, and we got two methods for shrinkage. One is ridge, another one is lasso. So there's ridge regression, there is lasso regression. The ridge and the lasso regression are shrinkage technique. Okay, but let me tell you the difference between the two. Okay, you know, uh ridge, okay, we not shrink them to zero, unimportant, the coefficient of unimportant to zero, but it's still going to retain them in the model, except that their p-value will be greater than 0.05. They will not be significant. It's still going to be in the model. Okay, but lasso we said no, I'm not going to retain them in my model. I'm only going to retain the significant one. This is the difference between the two now. The two of them are method of shrinkage. The ridge will still retain unimportant variables in the model, except that their p-value will not be significant. But lasso, we say, since they are not significant, they are not going to appear in the regression output. Does that make sense to you now? Okay, now we got the advantages of shrink, of the advantages and disadvantages. Okay, the advantages or disadvantages of them. Okay, they will reduce variance. Reducing variance. Initially the variance was high because there's so many variables. Okay, and this technique will reduce, whether ridge or lasso, they will reduce variance. But what is the disadvantage? Oh my God, you cannot eat your cake and have it. It's going to reduce variance, but it's going to increase bias. And you know what? Bias is the enemy of any scientist, any economist, any psychologist, any statistician. Bias is our enemy. We normally, the reason why, when we are trying to, take a look at this, statistically, we are trying to reduce, when you are reducing bias means consider so many variables. What problem are you going to have? High variance. Okay, if you want to solve the problem of high variance now, removing that will lead to what? Problem of bias. And that is the reason why later on we're going to talk about trade-off. We need to have a trade-off. Okay, now, dimensionality reduction, I just talked about it. We use this to reduce, to solve the problem of multicollinearity. When you have situation where explanatory variables are correlating, and you are now looking for a way to reduce the dimensionality. The advantage of this, okay, you're just going to, and that regression technique is called principal components. Has anybody heard about principal component analysis? Okay, principal component analysis is a way to reduce the dimensionality, in regression model, where we're trying to solve a problem of multicollinearity. Okay, and it's also an approach to convert variables that are explanatory variables that are correlated to uncorrelated. Okay, so but the advantage of this, a much smaller model, you're going to have a much smaller model because it reduces dimension, faster to fit, the coefficient will be stable. Okay, because when there's a problem with OLS, the coefficient will not be stable. Instability of coefficient is not good. Does that make sense? Okay, what is the disadvantage of this? Okay, the relationship between Y and S is not taken into consideration because we are only focusing, using a dimensionality reduction, we're only focusing on the explanatory variables. Okay, and that's not good. Okay, then original variables will no longer be in the model. Okay, therefore the interpretability is lost because, and that is what we did yesterday on the polynomial regression. In a polynomial regression, because S squared depends on S, there's a problem of multicollinearity. How do I know? The VIF of each of them is greater than 5. What do? We use the method of centering. right? When you use the method of centering, even in principal component analysis, we also use the method of centering. And with that interpretation, because you have a new variable now, you see the way we interpreted. Eventually, we were focusing on the mean because we actually believe a random variable, explanatory variable S was close to the mean of that. Does that make sense? Okay. Now, subset selection. I've talked about Shunke technique. I've talked about dimensionality reduction. This is another approach that we call subset selection. In a subset selection, okay, let me quickly tell you this. We have three types of subset selection. That's what we call forward selection. Forward, we're going to start from the simple model. Start from intercept, add one, okay, add two, until you stop. That's a forward selection. Then we have backward elimination. You know what we mean by backward elimination? You start with the complicated model with all explanatory variable. Then you're going to be going backward, eliminating the insignificant one. That's a backward elimination. And the last one is what we call stepwise. The stepwise is when you proceed in both directions, you use a combination of the forward selection and the backward elimination. Okay, that's what we mean. Now, those are the three approaches we can use. Now, I want to go into model complexity and model fitness. Okay, let me tell you this. Model complexity, we got two criteria that we normally consider for model fitness. The two criteria are residual sum of square and R squared. Okay, whether I said for model fitness, if I want to know whether my model is is adequate for the relationship I'm hypothesizing, okay, there are two criteria we use: residual sum of squared and R squared. When the residual sum of squared is very small, or when R squared is very high. But let me tell you this: that model fitness is only good for situation where the number of explanatory variable is not more than 3. If the number of explanatory is more than 3, you cannot use ROSS and R square. You can't trust R square anymore. Okay, in that situation, you now need a brand new criteria that will combine both model fitness and model complexity, because your model is becoming complex because you got a lot of parameters in the model. Okay, now the brand new criteria that we use: number 1, adjusted R squared; number 2, AIC; number 3, BIC. Okay, I'm still going to discuss all of that. Now, take a look at this guy. Between model fitness and model complexity, we want a model that fits the data well, and we want that model to be relatively simple. Why? Why do we want it to be relatively simple? Because we want our model to be interpretable. Because we have so many interexplanative variables in the model, the interpretation is going to be lost. Okay. Now, what are the criteria? RSS or R squared? Those are the criteria that we use for model fitness. Okay. I ask a question here. Does RSS mean the model fit the sample data better, smaller? Don't forget, RSS means unexplained variation. And larger R squared means the model fit the sample data better. Does that make sense? Okay, now K is the number of regressors. The more you have the regressors in your model, the more the model becomes complex, right? Okay, now what does smaller k mean? Smaller k will mean a model is simpler. Smaller k means, so I only got few regressors in my model. Okay, so take a look at that. Now, I need you to take a look at, I'm going to show you a picture right now. And I believe I've shown you this picture before. Okay, let's start with this. The middle one, okay, intercept model. The number, we only have one regressor, k equal to 1. RSS is high, right? That's a bad fit. Even if it is very, very simple, that's a bad fit. Okay, if you look at the first one here, okay, the first one here, where for simple linear regression, where k equal to 2, you see the R squared. And the other one, take a look at that one. How many regressors do we have? We got so many regressors. Okay, we got five, right? Five regressors. What is the RSS? Zero. We don't want that. That's a perfect model. Okay, that's a part. You know why is it a perfect model? Because there's so many regressors in your model. You see so many regressors. Okay, now take a look at this. So which means, in this kind of situation, we cannot trust this RSS. Okay, because let me tell you this, RSS does not put into consideration model complexity. It's just for model fitness. And that's why we need a brown new approach that we, combine both model fitness and model complexity. Okay. Now, I wanted to say something here. What is the reason why we cannot trust R square when the numbers of regressor increases? Okay, even if regressor you are introducing does not make sense, R square is going to go up, and that may mislead you, right? Now, I'm going to show you something now. Take a look at what I'm displaying now. Or take a look at what I'm displaying now. Okay, when look at the R square here. Look at the R square. When we continue to go, what happened? R square is increasing. Does that make sense? Now, when you take a look at this, and I ask a question, how did RSS change when we had more polynomial regressors? It's going to be decreasing. And how did R square change when we had more polynomial regressors? It's going to be increasing, even if what you are adding does not make sense. And that is the reason why when your model is becoming complex, we need a brown new criteria that will combine both model fitness and model complexity. You cannot trust, RSS or R square anymore. Does that make sense? And what can we trust then? We need to have a brown new criteria. Okay. Okay. And that was why I said the criteria need to consider both fitness and complexity, not only fitness alone. Okay. And what are these criteria? Oh my God. These are the criteria. The criteria number one is adjusted R squared. Adjusted R square can be trusted, which means uh, adjusted R square was a way of modifying the conventional R squared. Does that make sense? And let me tell you this, the AIC that we call a Kaike information criteria and BIC, the Bayesian information criteria, the model with the smallest AIC is the best. The model with the smallest BIC is the best. Okay? Why the model with the largest adjusted R squared is the best. And let me also tell you this. At times, there could be conflicts between these three criteria. Okay? Now, let's look at the formula of adjusted R squared. Okay, oh my God. Look at the formula for adjusted R squared. It's a modification of RSS. Do you see RSS in this formula? Don't forget, RSS was part of criteria for model fitness, right? If you want to get a brand new criteria that will combine both model fitness and model complexity, then you need to adjust the RSS. And that is why in this formula now, you can see RSS as part of the formula, right? Okay, this is the formula for adjusted R squared. Okay, the RSS is a pseudo sum squared. SS total is the total variation, and N is the number of observation, and K is the numbers of regressors. Is there any question at this time, whether in person or online? Any question at this time? Okay, now I have a question here. As you increase K, what will happen? When I increase the numbers of regressor, can somebody tell me what will happen to sum of square total? What will happen to the total variation when I increase the numbers of K, the numbers of regressors in my model? Eh? Somebody said something. No, changing, right? Send me a message for extra credit. Because total variation only has to do with response variable. Even if you are adding explanatory variable, it's not going to change that variation. Does that make sense? Okay, so then n minus 1, what going to happen to n minus 1? Don't forget n is the number of observation. If you are adding explanatory variable, what will happen to the number of observation? Also not changing. Send me a message for extra credit. Then what is going to happen to RSS? RSS is going to change. Oh, what is it going to be? When I'm adding more regressors, RSS is it going to be increasing or decreasing based on what I've shown you before? Whether in person or online, it's going to be decreasing. Look at it here. I'm going to go back and for you to see. I showed you earlier. Okay? Look at the RSS. When you are adding regressor, what happened? It's going down. Please take notes. What happened to the R square? Going up. Please take notes. Those are the kind of questions that may come up. Okay? These are the kind of questions that may come up. Okay? Then what about I minus K? Something like that. Okay? Pay attention to all of that. Now, but you know what? We normally select the model with the largest adjusted R squared. We believe the model with the largest adjusted R squared is going to be the best. Let's go to the second criteria, AIC. Oh my God. In the formula for AIC, what do you see? RSS. All these brown new criteria, they are just having a mathematical way of modifying RSS. Does that mean saying the RSS residual sum of square I told you the other time, a criteria is a criteria for model fitness only. Okay, if you modify that, okay, it's actually going to give you something that is going to be a brand new criteria that actually combine both model fitness and model complexity. Okay, this is the formula. Very easy, right? To compute. The moment you have RSS, what is your N? Number of observation. What is your K? The numbers of regressors. Okay. Now, you can also answer that question, but I'm not going to go there right now. The rule of thumb: select the model with the lowest AIC. Now let's go to BIC. Now. Okay. Now, let me come back here. Take a look at this guy. That's an R code. If I want to get an AIC in R, extract AIC. You know that thing that you used to name your model, like yesterday M1, right? Okay. Just extract AIC. Okay. Now I'm gonna go to the BIC now. I'm gonna go to the BIC now. Oh my God! Look at the BIC. BIC also. What does he have in the formula? RSS. So the three brown new formula, they were just modifying the residual sum of square. Okay, take a look at that. Okay, now here, the rule of thumb is to let the model with the lowest BIC. And how do I get that in now? Oh my God, please take a look at this. If I want to get a BIC now, I'm going to take extract AIC. The model name, I'm going to get K equal to that. K equal to log of N. That's an R code for that. Take a look at that. Okay, so that is the criteria, right? Now you know what I want us to do now. Do you know when you run a model? Maybe you actually you want to look at the effect of experience on the salary of professional workers, and you got four competing models. What is the first model? Linear model, right? Okay, the second model, quadratic. The third model, cubic. The fourth model you can see. So the polynomial, at times you could be thinking whether you should fit a polynomial of degree 1 or degree 2 or degree 3 or degree 4. If you decide to fit all of these, okay, now you cannot use RSS and R square to compare this. Why? Because you are comparing between models that involve a high numbers of regressors. And what are you going to do? You get the AIC for each. You get the BIC for each. You get the adjusted R square for each. But let me tell you this, there could be time where there may be conflict among AIC and BIC. Don't forget, the AIC, the BIC, and the adjusted R square, they are like different judges in the different courts. Different judges in a different court. And that is the reason why we can never have one judge in the Supreme Court. There's going to be like more than one judge. Does that make sense? And they're going to use the idea of most popular decision. Okay? And even the reason why I like the justice system in the United States because of even in the lower courts that they have one judge, they also have juries, right? Jury system. Okay. Now I need you to take a look at this. What is the model with the highest adjusted R square here? This guy, right? What is the model with the lowest BIC? Okay, is it this guy? What is the model with the lowest AIC? This guy, right? What happened here? Agreement occurred between AIC and BIC, right? Conflicting with that. You know what we're going to do here? We will go with the AIC and BIC. Can you see that, right? Okay. Then, so now, and do you know another reason why we go with the AIC and BIC? The model they choose is not even complicated. They actually choose a polynomial of degree 2, right? Why they just allow square choose a polynomial of degree 3? Go ahead. Oh, okay. Most of the time, they're always going to be the same. Most of the time. Does that make sense? Between AIC and BIC. But statistically speaking, we trust AIC be the more. That's how you're always going to hear AIC, 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 AIC. It's very, very popular. Okay. Now, I've already considered all of that. Now, you know what I want to do now? I want to go into selection method. Selection method is different from the criteria for selection. We're just talking about criteria. We now want to talk about selection method. But you know what? In the selection method, that we have different method. We have of subset selection versus stepwise selection. In each of the selection method, we're going to we can be making use of any one of these criteria to judge. Does that make sense? Okay, now let's get started. With the first one, please, I need you to pay attention. I want to fit a model. Okay, in the model, I got 3 explanatory variables. Please pay attention. I got 3 explanatory variables. You know what I'm going to do? I'm going to first specify the complicated model that is going to be there. Then I'm also going to specify the simplest model. Okay, what is the simplest model? Intercept model. And the most complicated. The most complicated will contain all the possible explanatory variables you want to think about. Does that make sense? Now, you know what I want to do now? I want to consider all subset selection. Oh my God, in the all subset selection, I'm going to use the idea of a power of a set in mathematics. You know, in mathematics, power of a set, okay, it is 2 raised to power cardinality of a set. You know what I mean by cardinality of a set? Cardinality of a set means the number of elements in a set. If I have 3 elements in a set, if I want to talk about power of a set means the possible subset in a set. The possible subset including the set itself and the empty. And that will give you, situation where you got 3 variables, that should be 2 raised to power 3, right? That is going to be 8 models. Which means if you want to consider of subset selection, okay, the possible number of subset selection you're going to consider is going to be 8, which I'm going to show you right now. Okay, which I'm going to show you right now. Oh my God, that is the 8. Look at the first one. 1. That's 3. Another 3. Another 1. Making how many of them? 8. That's it. 2 raised to power 3 is 8. And the power of a set is going to talk about, is going to include the complicated model itself is a set and empty. That's going to be 8, all of that. Okay. And you know what? All subset selection will mean we have to go through each of these to be able to identify the best model. That's what we call all subset selection. Okay. it is this approach. It's actually the strength is that you'll be able to go through all possible model, but the weakness is going to be computationally expensive when K is large. Imagine when you have 10 explanatory variables, that will be 2 raised to power 10. That's going to be a lot of subset. Okay, now, here now, I'm going to show you. Now, that is what we call all subset selection. And we can use, if you can, we can fit all of that. You know what you're going to do when you fit all of that? You get the AIC for all of them. The one with the smallest AIC is what you're going to choose at the end of the day for subset selection. Now, let's go to the stepwise. In the stepwise method, we are backward. Now, please, I need you to pay attention. I want to explain how do we do backward, how do we do forward, and how do we do both. Please pay attention. You know, with the backward elimination, what did I say? We're going to start with the complicated model, right? Then we're going to be eliminating, right? Until we get to the optima. Please pay attention. Okay. Now, I'm going to give you an example. If I want to do backward elimination, I will choose one of the criteria. Do I want to use AIC in it, or BIC in it, or adjusted out squared? Does that make sense? Now, how do we start with the backward? We start with the complicated. Did you see complicated here, right? We feed a complicated model. We get the AIC. Okay, we get the AIC. AIC is this. You know what? You know the next thing we're gonna do after the complicated, we're gonna go into the where we go from 3 variables to how many now? 2. What are the possible 2? Please pay attention. Oh, in the step 1, I'm actually gonna have 3 possible. Is that not? Possible 2. The first one is use the complicated, right? The second step means possible 2, right? Get the AIC, okay? And you know what? You know what we're going to choose? In the second one, we're looking for a model that will have a AIC that will be lower than this, okay? Now, what is going to happen now? Please pay attention. This is very, very crucial, okay? Now, what happened here? Is that not the lowest? That one is lower than negative 112, which means right now we're gonna drop the complicated, and out of the 2 possible, that guy is what we're gonna choose now. Any question on that? Now, you know, right now, oh my God, right now we are here, right? What is the next step? In the next step, we're going to choose a module that have just one variable. And that one variable has to be x1 and x1 only and x3 only. Do you see that? This will lead to this. You see that? In that very module, do you see x1 and x3, right? I'm going to consider x1 separately, x3 separately. Then I'm going to find the AIC. Okay? Now, is there anyone that have a AIC smaller than the 2? Yeah. Negative 121. Okay? Now, according to the backward elimination now, which one is the best? Which one did they choose? Okay, finally, okay, you know, the moment you have this guy, what is the next step? There you consider module without any variable, which is going to be like step 3 here is going to be situation where there's no explanatory variable. What do we want to do? We want to see whether that module will be better. But what happened now between the two? Is intersect module better? No. Therefore, what is the optimum module? The optimum module is this guy. Any question? Well, I'm done. Wish me the best module. Okay. Going by backward elimination is that fitting a model with S3 because it's the best. That is how backward elimination works. Is there any question about this backward elimination? Go ahead. Oh, okay. you are trying to talk about, oh, okay, so you're trying to talk about what informed the decision to choose either backward or forward, right? Oh, okay. But you know what we do? We try all of that. And at times there could be conflict. I'm going somewhere to, I'm going to say something when we get here. There could be a conflict. You know, here now, backward choose, model with history, right? Now, let's see the way forward is going to work. Are you going to see something now? Okay? You're going to see something now. Now, forward right now, we start with the smallest. Don't forget, we start with the model without nothing, without explanatory variable. Then from there, we're going to go to 1, right? Is that surprising? No, forward. Forward, we start with nothing. This is nothing. Don't forget forward. Start with nothing. Start with the intercept model. To, what is the next one? One variable. Okay, one variable, S1, S2, S3. Does that make sense? Now, which one has a AIC lower than that? Okay, if you take a look at it, negative 125, right? So based on this, you will now go to 2, right? If you're going to go to 2 variables, but the 2 variables you're going to go into must have S2. You know, you can see S2. Now, what are the variables that must have S2? Take a look at that. It's only going to be this and this and S2 and that. It must have S2 because S2 is in the where we are right now. Does that make sense? That's super cool, right? Now, after that, look at the look based on that now. Which one is smaller than the way we have between this and this? Is there anyone smaller than that? No. Then the forward elimination is selecting that. Okay, the same question, the same data. Okay, now what do you think? What do you think happened? Okay, forward. Give me 1 second. Forward, select this guy, the model with S2, but backward, select the model with S3. Okay, huh? Exactly. Now, take a look at this. Yeah, you're right. Now, you know, the disadvantage here is that the backward elimination miss this guy. He did not even consider that at all. And this guy is a model with what? With the lowest AIC. That is the disadvantage of using a backward elimination. And that is why in statistics, we normally start from the forward, start from the intercept, adding 1, and continue to go like that. Does that make sense? Okay. Now, how many module do we consider in this backward? You can count the numbers of module you consider. But if you want to talk about how many module do we consider in general, okay, you are always going to use 2 raised to power numbers of predators. Now, I've shown you all of that. Okay. And let me tell you this. When you want to talk about stepwise method, okay, strength, computationally efficient, but weakness, in some cases may miss out the best model, just like what I just showed you. And it's just like you have 2 road diverging in wood, and I took the one less traveled by, and that has made all the difference, according to Robert Frost. Okay, you know what I put here? This is what my TA is going to walk you through on Friday. How do we do up-success selection in R? You know, we talk 4 of us out with the up-success selection, where you consider all the subset of the modules. Okay, how do you do that in R using AIC? Okay, my TA is going to walk you through that. Now take a look at this. Okay, do you see this? Okay, you can see which one is the best here, which one is the best AIC according to the best here. That, okay, my TA is going to walk you through that. How do we do backward elimination in R? Okay, look at that. That is the code. My TA is going to walk you through all of this. How do we do the forward in R? These are the code that my TA is going to walk you through on Friday. Okay, if you take a look at this, you're working on the same data rate my professor, and you consider some variables, and by all subset selection, You want to compare the module ancestor selection choose compared to the module forward selection choose compared to the module backward elimination choose. Okay, in statistics, we normally have options, and it's better we have a lot of method, and we're only going to compete. We're going to choose the best at the end of the day. We got a criteria for choosing the best. Okay, my TA is going to walk you through all this. Now, before I go, today I've introduced you to what I'm actually call variable selection. We don't just add variable into our module because just for adding sake. No, we're actually going to put into consideration some techniques, and that was why I said there are three. I first identify ways under which OLS can be used and situation where they cannot be used. When the OLS can be used, it's going to perform greatly. It's going to turn out low bias, low variance in a situation where the number of observation is much more greater than the numbers of regressors. Situation where the number of observation is very close to the number of regressors, or the number of observation is even less, then you don't expect your OLS to perform great anymore. If you use OLS, you're actually going to mislead. Then what are we going to do? We got three ways to resolve this. It's number one is either we go by subset regression, okay, approach, or we go by method of shrinkage. Okay, in the subsequent lecture, you're gonna hear us talking about how do we do lasso regression, how do we do ridge regression. The lasso and the ridge regression, they actually gonna help us to shrink, the coefficient associated with an unimportant variable, to zero. No, the ridge is not going to shrink it to 0D, but they're still going to be retained in the model, but the p-value is not going to be significant. But why for lasso regression? The lasso regression will completely eliminate unimportant variables in the model. Okay, then another approach is when you talk about dimensionality reduction, where we make use of principal component analysis. Okay, now what I've just walked you through is the ancestor selection approach, where we make use of the forward selection, the backward elimination, and so on, like that. So this is a way to select. And I also remember I actually said we got criteria for model fitness alone, which is the ROS, the residual sum of square and R square. And I said the moment your model is becoming complex, where if you have numbers of regressors is more than 3, okay, then you cannot trust your ROSS and R square anymore. Okay, then you need a brand new model selection criteria that will put into consideration both model fitness and model complexity. And what are these brand new criteria? The number one is adjusted R squared, and number 2 is the AIC, number 3 is the BIC. And I said you're actually going to choose the model with the highest value of the adjusted R squared, and you're going to choose a model with the lowest. And there's possibility we could have situations where there could be conflict among them. And I want to believe AIC and BIC agree most of the time. Is there any question before I go today? Okay, make sure you all stay safe and have a lovely day. Bye for now, everyone. Viola, you have any question to ask? Okay, you're super cool, right? Okay, make sure you stay safe as well. Bye for now.
Thank you.
You're welcome.